Okay, now let us move forward to page 434, question 6. So the question says, determine whether each of the following half reactions present in an oxidation or reduction supply the correct number of electrons to balance the equation. So the first thing that I'm seeing here is that this equation has a two-part answer. So it wants two pieces of information from you. The first one is that it wants us to identify whether it is an oxidation or reduction. And the second one, it wants us to supply the correct number of electrons to balance the equation. So the first thing I'm going to do, because I've seen the word oxidation or reduction, is I'm straight away going to write oil rig. Now, as we look at our first equation down here, we've got copper 2 plus going to copper 1 plus. Now, the next thing that comes to mind is that we can see that our charge is changing from +2 to +1. Now, remembering that redox is the movement of electrons, and we know that electrons are negatively charged. So, because +2 is going to +1, we can see that the charge is getting more negative because it's decreasing. So, because the charge is getting more negative, it means it must be gaining more electrons, okay? Because electrons are negatively charged. Now, what that means is that because the charge is going down, it's getting more electrons. We remember that reduction is the gain of electrons. So that means this equation here must be a reduction. Now, this answers the first part of the question up here. The next thing we need to do is we need to supply the correct number of electrons to balance the equation. So that's very important, is make sure that when you answer a question, especially under exam conditions, to make sure that you go back and you reread the question to make sure that you answered all elements of that question. So we've identified it as a reduction. We now need to look through and we need to supply the correct number of electrons. So we can see here that we have +2. Then we have an arrow, so some sort of reaction happened, and then the charge went to +1. So we can see from just writing it out like this, that the electron must be on this side. Because we know the electrons are negatively charged, and because there is a missing charge of 1, we know that this must in fact be -1. Because if we had -1 plus 2, that would give us +1. Okay, so we know the electron should be here. Now we have a look at our next half reaction down here. So we've got 2iO4 minus plus 16 hydrogens will go to I2 plus 8 H2O. Okay, this one looks like it's a little bit more tricky. The first thing we need to do here is we need to compare our iodides. Now, this makes it very hard for our compound here because oxygen is hiding it, okay? Oxygen's sort of getting in the way. Now, how we can get around that, how we can combat it, is via the use of our oxidation numbers. So we know that oxygen has a charge of -2. And we can see here that we have 4 oxygens. So we know that the overall charge for our oxygens here is -8. Now, when we have a look at the overall compound, we can see via here that the charge of the overall compound is -1. So this is where we ask ourselves, okay, what is the charge of iodide if oxygen is -8? And the answer is it must be +7. Because all of our oxidation numbers must add up to form the overall charge. So because oxygen is definitely -8 and the overall charge is -1, we know iodide must be -7. Now, something that's very important here as well is we need to pay attention to our coefficient down the front. So we know we have 2 lots of iO4 minus. So in order to make our equation equal, because we can see there are 2 iodides on the right, and we've only found the charge of 1 of our iodides here. So because there are 2 lots of this compound, we know that the total charge must be 14 because there's 2 lots of these iO4 minus. So now we compare our iodides here and here. Now remembering too with our rules of our redox equations in that if you've got a diatomic molecule, something that's bound to itself, its overall charge must be 0. So we know the charge of I2 is 0. So again, we compare, we've got plus 14. That's then going to 0. So we know that that is a lower number, so it's getting more negative. So it means that this must be a reduction because it's gone from plus 14 to 0, to neutral in charge. Now, again, we can write plus 14 to 0. So which side would we put the negatives on? We would put the electrons, which are negative, on the left-hand side. So we would put minus 14 plus 14 will equal 0. So therefore, our 14 electrons must go here. Okay, now let us look at page 435, question 14. So balance the following redox equation. Okay, so here we go. The first thing I'm going to do is, again, I see the word redox. Straight away, I'm going to write oil rig. Now, the next step I'm going to do is I'm going to break this reaction down into its half reactions. Okay, and I'm going to write that just up here. So I can see we've got ClO3 going to Cl minus. So I'm going to draw a line there, and I can see just my single iodide going to iodide here to I2. So I'm going to draw a line there, and those are our half reactions. Now, something you need to be aware of too in more complicated equations is you're going to have what are called spectator ions. Now, these are ions that are that will be involved in your chemical formula in here, but don't actually take part in the reaction. So with this particular example, we do not have any spectator ions, so it's made it a lot easier for us to identify our half reaction. So I'm just going to write that up here. So we've got I minus. Okay, now the next thing I'm going to do is I'm going to identify whether this is being oxidized or reduced. Now we can do this by looking again at our charges. So we can see here the charge of iodide here is -1. The charge of iodine here is -1, whereas our iodide, which is the I2, is neutral in charge. Because again, going back to our redox example, our rules rather, we know that if we have a diatomic molecule, it is neutral in charge. So here, this is quite negative, and it's going to neutral. So it means it's getting more positive. So if it's getting more positive, it means it must be losing electrons. So going back to our example of, if you've got a lot of debt and someone takes some of that debt, you get more wealthy, you get more positive. So we know that this is being oxidized because remember over here, oxidation is the loss of electrons. So this is being oxidized. So we look again at our half reaction and we can see that we have chloride on the left and a chloride on the right. But the problem is that we cannot compare these two just yet because oxygen is getting in the way, okay? It's being a bit of a nuisance. And again, this is where our oxidation numbers come into play. So what we do is we know that oxygen is -2 and we have 3 oxygens. So the overall charge must be -6. Now, because all oxidation numbers must add up to the overall charge, we know that the overall compound is -1. So chloride must be something, so it's chloride plus -6 will give us -1. So it means that the chlorine here is +5. So now we can successfully compare our chlorines here. We compare our chlorine over here to our chlorine over here, and we can see there is a difference of 6. So we know that 6 electrons are moving between our ClO3 minus and our Cl minus. So because this is getting more negative, it means that it is gaining electrons, which means it's being reduced. So we've got one that's being oxidized, we've got one that's being reduced. So our next step is we're going to balance our oxygens and our hydrogens. So what I'm going to do is I'm just going to rewrite the equations down here. So now we're going to balance our oxygens and our hydrogens. So we can see on our initial reaction up here, there are no oxygens, there are no hydrogens, so it's fine. We can leave that as is. We can see, however, on our next half reaction is that we have 3 oxygens on the left and 0 oxygens on the right. So our next step to balance that is to add water. Now this is a very important part. Please do not add just oxygen. You must add water, okay? So because there are 3 oxygens here, it's going to be plus 3 H2O. So that is now going to make our oxygens balance because we've got 3 lots of oxygen, 3 lots of oxygen. Now that we've balanced our oxygens, we must balance our hydrogens. So we can see with our first half reaction, there are no hydrogens, so we're fine. But with our second half reaction, we have 3 lots of H2, which means there are 6 hydrogens on the right-hand side. So we must balance those hydrogens on the left-hand side. And we can do this simply by adding hydrogen. So we can go 6H+. Now, because our hydrogens and our oxygens are now balanced, the next thing that we need to do is balance our movement of electrons. So in order to balance our movement of electrons, we're going to be looking up here again. And we can see here, so if we have a look, we have -1. So we have -1, so that's 1 electron, but it's going to a neutral charge. It's going to 0. So how many electrons are being moved? And the answer is 1. Okay, we can see here we're going from -1 to 0. The overall, how many electrons moved is 1 electron. Now, if we look over here, we can see that we have +5, and +5 is moving to -1. So we can see that over here, we have a movement of 6 electrons. Now, this is where, again, we have a bit of a problem, because how can it be that we have iodide losing 1 electron, and yet we have a chlorine atom that is gaining 6? So it doesn't really make sense. If you've got someone who throws 1 tennis ball and another person catches 6 tennis balls, this is where we ask ourselves, well, where did those other tennis balls come from? And the answer is, they didn't just appear. It's more that we had 6 lots of people throwing 1 tennis ball each. So what we do is we need to balance these equations, and we can do that by multiplying them by each other. So that means that we multiply this top reaction here by 6, and we multiply this bottom reaction here by 1. So what I'm going to do is I'm going to rewrite that equation down here. Now you don't need to rewrite it this many times when you're solving this equation. I'm just doing it so you can see all of the steps that I'm conducting. And we're going to multiply the bottom equation by 1, which means it's going to stay the exact same. So we can see a bit of a problem here before we move on, and that is that we have 6 lots of I- up here. So that's indicating that we've got 6 lots of electrons. But over here we have 6 lots of I2. Now this has a neutral charge. It's a charge of 0. But our iodides aren't adding up. We have 6 on the left-hand side, and we have 12 on the right. Now what we need to do is we need to take this into account, and we need to change this 6 to a 3. Now, by doing this, this means that our iodides are now balanced, because we have 6 on the left and we have 6 on the right, but this did not affect our charge, because we can see that we still have an overall charge of -6 and an overall charge of 0. So be careful of that. That's a common trap as well. to make sure that all of your elements are balanced, as well as the charge. So we can see here that now we have balanced the number of elements, we have balanced the electrons, and we've balanced the oxygens and the hydrogens. So our next step is to do what I call the step. And that is very simply is this. It's 1, 2, 3. And what we're going to do is we're going to combine these two equations into one again. So we're going to write everything on the left with everything on the right. So now that we've combined our two half reactions into one, our next step is we need to make sure we don't have any double ups. Now be cautious here because again, this is another trap where students will go, okay, I have 6 iodines on the left and I have 6 iodides on the right, so I can cancel those out. And the answer to that is no, you cannot, because they are not the same thing. We can see here that I- is not the same as I2, okay? They have a different charge, they have a different number of electrons, and they are also combined in a different way, so we cannot cancel these out. The same goes for when we're looking at hydrogen. We cannot go, there are 6 hydrogens on the left, 3 times 2 is 6 hydrogens on the right, so we can cancel those out. You can't do that, okay? So we can see here that we actually don't have any double ups, so we can leave this as is. So now that we have our fully balanced and combined redox equation, I normally include one last step, because this is a step that tells you whether you got it correct or not. So what we do is we write the overall charges of all of our compounds and elements here. So we've got 6I-, so the overall charge is -1 times 6 is -6. 6H+, the overall charge there, +1, 6 hydrogens is +6. And ClO3-, the overall charge here is -1. So that means that the overall charge for the left-hand side gives us -1. Now, we look at our right-hand side, we can see our 3 lots of I2. Now, remembering these are neutral in charge. So the overall charge here is 0. Now we have 1 Cl-, so the charge there is -1. And 3 H2O, remembering that water is also neutral, so it is 0. That means the overall charge for the right-hand side is -1. So now we have a look, we have a -1 on the left, we have -1 on the right, and that means that we have a fully balanced redox equation. Okay, so let us now move on to our very last question. So let us now balance the following redox equation. So what I'm going to do again is we're going to split this equation down into its half reaction. So we do so by drawing our little lines like thus. And I'm just going to write it up here. So we've got, now again, remembering whenever we're doing our oxidation reduction reactions, we always write oil rig. And now we need to identify whether this is being oxidized or reduced. So again, we've got our pesky oxygens always getting into the way. So we have O7. So we know oxygen is -2 in charge. So we're going to we know the overall charge of our oxygens here are -14. And now we ask ourselves, well, we know that our oxidation numbers must add up to the overall charge. So we know that the overall charge is -2. So what must our CR be? And the answer is it must be +12. So now we compare our two over here, but this is where we have a slight problem. So we can see over here that we have CR2. So it means it's not balanced. So what we need to do is we need to add a 2 to make them balance. And that also allows us to compare them properly. So we can see here that we have CR2 has a charge of +12. Now we know that the CR over here has a charge of +3, but there are 2 of them. So it means the charge changes to +6. So we look at it now. So we've got plus 12 to plus 6. We can see that obviously the number is going down, it's decreasing, which means it's getting more negative. So because it's getting more negative and electrons are negative, it must be gaining electrons. So that means that this must be a reduction, and they are moving 6 electrons. Now we look down into our next one. We can see here that we have oxygen, and oxygen we know has a charge of -2. There are 3 oxygens, so this has an overall oxidation number of -6. Hydrogen over here is +1. There are 3 hydrogens, so this must mean it's +3. The overall charge is 0, which means our AS must be +3, because 3 plus 3 minus 6 equals 0. We look at our next one over here. We've got 4 oxygens, so 4 times -2 is -8. We have 3 hydrogens, so that is a charge of +3, which means that our element here must be +5, because 3 plus 5 minus 8 equals 0. So now we compare the two again, so we can see that we're going from +3 to +5, so it means we're getting more positive. So because we're getting more positive, we must be losing those negative electrons, which means that if we are losing electrons, we must be getting oxidized. So that means that this is being oxidized by 2 electrons. So now our next step is to make sure that everything is balanced aside from oxygen and hydrogen. So we can see here, because we've already done that step, because when we were looking at our charges, so our CRs are balanced, our AS is balanced, and everything else we don't need to worry about. So the next step now is to worry about those oxygens and hydrogens. So I'm just going to write that down here. So now we need to, of course, balance our oxygens first. Now remembering, we always balance oxygens by using water, not O2. So we can see here we have 7 oxygens on the left, we have no oxygens on the right, so that means that this must have 7 waters. So we can see here 7 oxygens, 7 oxygens. Now we balance our hydrogens by going 0 hydrogens over here, but we have 14 hydrogens over here. So we're going to put 14 hydrogens on the left-hand side. So they're nice and balanced. The next thing we do now is move on to our next half equation. So we can see we have 4 oxygens on the right, 3 oxygens on the left. So we add 1 H2O to the left-hand side to balance these oxygens. And we can see here we have 3 hydrogens on the right and 5 hydrogens on the left. So we add 2 hydrogens to the right-hand side, and everything is now nice and balanced. Now, here's what we want to do. We can see with these reactions, like what we wrote up here, that we have a loss. So what we can see, just from our reactions that we did up here, that our first half reaction, we had a gain of 6 electrons, because it was being reduced. And down here, we have a loss of 2 electrons, because it was being oxidized. So what we need to do is, to make our number of electrons equal out, we must multiply everything by the lowest common denominator. Now, here is a little student trap. So I want you to be very aware of what I'm doing during this step, because this catches a lot of people out. So we multiply this top part by 2 and our bottom half by 6. Okay, so here's the student trap. So we've multiplied this first half reaction by 2 and this bottom half reaction by 6, but that is not the lowest common denominator. Because if we've multiplied this one by 2 and this one by 6, there is still our common denominator, which is if we divide everything by 2. Okay? So what I mean by that is that everything in this equation can be further simplified. It's not as simplified as it can be. So how to fix this, because we can further simplify everything, is we need to divide everything in this whole equation by 2, and that will make it as simplified as we can get it. So now we can see that our half reactions are now balanced. So we have now balanced the elements, oxygen, hydrogen, and number of electrons. So the next thing we need to do now is the step. So we go 1, 2, 3, and we now combine our 2 half reactions. So the next thing we need to do now is we need to cancel out any double ups that we may have. So just by looking through here, we can see that we have 14 hydrogens on the left and we have 6 hydrogens on the right, so they can cancel each other out. And that means that's going to leave us with 8 hydrogens. We can also see that we have 3 H2O on the left and 7 H2O on the right, so these will cancel each other out. And that's about all that can be cancelled out. So I'm now going to just rewrite this, make it a little bit neater. Okay, so what we do is now we need to do our final self-check step. So we look at our final equation here and we count up the charges. So we have 8H plus, so that is plus 8. So we have one compound that is -2, so that is -2. And this compound here is neutral. So we have an overall charge of +6. Now 2Cr3+, so we have a charge of +6. Water is 0, and our final compound here is 0. So the overall charge on the right-hand side is +6. So as we can see, we have +6 on the left, +6 on the right. That means we have a fully balanced redox equation. Okay guys, so that finishes up Module 7 Video 2. Thank you very much for joining me today. I know that was a bit of a full-on tutorial. If you do have any questions, queries, or suggestions regarding these tutorials, please feel free to send me an email at b.grant@griffith.edu.au. Now, if you could all please just complete the survey down below. I've just got a small link there. It's like 4 questions. It doesn't take very long at all, and it really helps me out a lot in getting some quality feedback from you guys, and helps me to improve these videos that I'm making for you guys. So my name is Brock Grant. Thank you very much for joining me today, and I'll see you next time.